Agriculture is a necessary part of human life. Farmers provide us with the food we need every day to survive. In the Chesapeake Bay, farming operations make up about 30% of the region. Although necessary, agriculture is also the highest contributor of nutrient and sediment pollution in the bay. This can lead to an overgrowth of algae, which disrupts the entire ecosystem and its inhabitants. Poor irrigation, over-tilling, and over-applying pesticides and fertilizers are all contributing to this problem. In order to meet its pollution reduction goals, Virginia must be able to identify farmland areas that are contributing to this problem.
So John, how do we solve this problem?
To address this problem, we trained a fully convolutional neural network, or an FCNN, to perform semantic segmentation on images containing agricultural fields. Using existing Virginia waterway data and satellite imagery, this would allow our model to identify agricultural fields close in proximity to waterways that lead to the Chesapeake Bay. Now let's see how this works. Semantic segmentation is the process of partitioning an image into multiple segments based on classes. For example, a model that performs semantic segmentation will typically output labels similar to what is seen here, given a standard image. This technology is extremely useful for applications such as medical imaging, self-driving cars, and in our case, classifying regions given satellite data. To perform image segmentation, a model referred to as a fully convolutional neural network is used. A fully convolutional neural network is similar to a standard convolutional neural network, but it uses an encoder to decoder structure to classify each pixel in an image as belonging to a specific class. As you can see here, the model architecture we use starts off as a standard CNN, but then reaches a bottleneck and starts growing the image back to its original size. This particular model architecture is referred to as the SegNet architecture, but we also experimented with models referred to as UNets and mask RCNNs that use similar principles. To train our model, we use an existing agricultural segmentation dataset provided by the Denmark Land Parcel Identification System. The dataset provided 4,691 images of agricultural fields in Denmark, as well as labels of the agricultural fields within the images. Here are examples of what the images and masks in the dataset look like, as well as a glimpse of the predictions generated by our model. Note that the masks seen here are only two colors because our application only involves binary classification. If we were predicting more than one class, the masks would be a lot more colorful like the image seen before. After pre-processing the data, we were able to feed it into our model to start training. Now let's take a look at the results.
Results of our final model were quite promising. The model achieved a 94% pixel-wise accuracy on the training set and 85% pixel-wise accuracy on the validation set. In image segmentation problems, another common metric used is mean intersection over union. Our model obtained a mean intersection over union of approximately 88% on the training set and approximately 86% on the validation set. If we wanted to improve our model's performance, the next step would be to collect more training data and also create a labeled data set of Virginia farmland to ensure our model is trained and tested on the same distribution we intend to use it for.
That's all for now, and thank you for joining us on Consider the Following.
Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter. T minus 7 seconds.
Bill Nye the Science Guy.